He's getting you. All right, welcome back, folks, to another exciting week of Colloquium. You have the great misfortune of having me introduce the speaker for the second week in a row. So I'm going to start off with a do-over of my introduction of Bethany Ellman from No, I'm just kidding. I'm not going to do that. We're really excited to have Christoph Keller here, who is the current director of the National Solar Observatory, which is headquartered out on East Campus in the Space Sciences Building, for those who haven't been there. Christoph was a PhD student at ETH Zurich, and after completing his PhD there, he moved to Tucson for a postdoc, but then ensuing research position there for about 10 years. And then back to Europe again, this time to Leiden, where you were for many years, 17-ish years. And then currently you're in your second year as the director of NSO. In addition to solar physics type questions, Christoph works on a variety of problems that touch many different fields of astronomy. And I think I will let you tell him more on his own. So with that, let's welcome Christoph.
Let's see. I think you can hear me. Does this work here? Okay, fabulous. So I'm talking about fun I have had in the past. I'm still having some fun, no worries. So also introduce myself in a very different way. I've been married almost 28 years to my wife, Rennie Galindo. We have 3 kids, 2 live in the Netherlands. 1 just started at CU Boulder here, the youngest. 3 cats, 2 dogs, 1 house. And hobbies, like nature photography, like woodworking. Not right now. No time for that. But really, this is not so much about me, but this is about all the grad students and postdocs that have worked with me. I'm very proud of them. A lot of them have made their way into different positions, from directors of astronomical institutes to high-level positions in industry. Really, what I'm going to show you is what they have done. So it's always been a great pleasure to work with young people. I'm going to talk a little bit about how I look at doing science. And as you will see, I'm not your person who works on a problem for all his career. I tend to jump around doing different things. And so I'm going to show you some of these things and try to show you the connections between these things. So I'm not a fan of logical and linear thinking. Really, breakthroughs, in my opinion, come from when you go crazy. And so for students, if you ever want to, I actually have a 12-step program how to become a crazy scientist. And this is kind of the short version of it. So the other thing is kind of, you have textbooks and tools and whatever. I tend to forget those. A colleague of mine once said that, 3 weeks in the library kind of cost him 3 years of his career. Sometimes not knowing, sometimes being innocent, and also just being new into the field, being young, not knowing about all the baggage that I drag around with me is a good thing. Just to, really think outside of every box. And I'm trying to show you a little bit sometimes where my thinking has gone in that way. Really, the way I try to look at things is as a system, not as an individual issue. I think astronomers are particularly good at doing that. I've seen many astronomers like Frank Schuh, very famous astronomer, went into energy science. The whole issue of how do you deal with energy, how do you make it sustainable, which is not a simple problem of just creation and consumption. And so I like to look at things as a system, and you'll see this coming back, where by thinking about it as a system, you get significantly better results than if you try to optimize individual things. So I have tried to, use an approach like this in many areas. When I did my master's, I could have finished in, I would say, almost bloody theoretical physics, really just paper and pencil. I thought it was interesting, but it was just, in the end, quantum field theory. I really didn't want to take the exam. But so I've done a lot on this theory side, which ultimately was helpful again, and I'll show you that. And then I very rapidly got into instrumentation. How do you actually measure things? How do you do things? I've worked in astronomy, solar physics, nighttime, worked in remote sensing, biomedical imaging. Wherever there is a really challenging problem that tickles me, I'm going to work on it. At least as a prof in the Netherlands, there was a big benefit of nobody telling me what I could do or what I could not do. I really like that. I've done, obviously, academic research, but also expanded into citizen science. Very interesting. We did good stuff there. And then maybe from, I've been teaching for a long time. At some point, you have it somewhat down. Maybe it's not good, but at least you feel like you're comfortable doing it. And what I find interesting now is managing people. Science is easy because it's logical. You can put in math and so on. People are very challenging. There's nothing necessarily logical about it. Everybody is different. And I actually have to say I enjoy that challenge. It's a very different challenge, but I do enjoy it. So let me jump into some of the academic thing here. My thing always had to do with polarimetry, with measuring the polarization of light. And that's simply fact that the electric field vector of an electromagnetic wave typically oscillates in a plane, or it does other funny things, like you can see here. At the top is linear polarization, where the E vector simply swings in a plane that is oriented in a certain way. Or then you can have circular polarization, where it goes like a screw. And then, in general, it's just some kind of ellipse that it does. Right? So this is additional information that we can gain. Measuring the polarization of light gives you additional information about where it comes from. And as you will see, in many, many cases, it is the way to learn something that you can't get in any other way. Early on, I started on something that was interesting because it was an instrumental challenge, and that has to do with scattering polarization. So when you look at the sun, to see how I see the laser. OK. So if this is the sun, and the shaded area is the atmosphere of the sun, photon comes from, let's say, the inside. It scatters off an atom or a molecule, and then goes out to the observer. As you probably remember, 90-degree scattering, that's typically very beneficial for getting a lot of polarization signal. So the question was simply, what can you learn when you look at the edge, at the limb of the sun, and measure linear polarization very accurately to pick up these scattered photons? And what we found was a completely new spectrum. It's now called the second solar spectrum, because it's full of things you would never expect. And it's just because the polarization contains that information. So from an astrophysics point of view, this is interesting. This is an intensity spectrum of the sun. And as you probably know, lithium is very rare in the sun. It's an older star. The lithium has basically burned up. And it's actually very difficult to measure lithium. I think the only halfway credible lithium spectra are from sunspots. When the temperature gets low enough, these lines here, they get fairly strong. So here is where the lithium line is. This little bump here is actually not the lithium. absorption, but it's some molecule that's close by. But when you look at the scattering, the lithium lines there, it's a resonance line. So it goes up from the ground level, up and back down. And those resonance lines tend to be highly polarized. And so what you actually see is exactly where the lithium line would be expected. You see this nice polarization signal here. It took theoreticians a decade or more to figure out how they could model this, but it's one way to actually directly see lithium on the sun. And that's because of the scattering. Now, if you look at the level here, this is a polarization level of 10 to the minus 4. The noise in here is at the 10 to the minus 6 level. That was really challenging. I like these kind of challenges. And we learned all kind of things, instrumental, optical effects. We had to develop new theories to calculate optics. All of that is now very beneficial for what we do with our 4-meter DCAS telescope, where that theory actually was used to design some of the elements to avoid issues when you do polarimetry like that. This one here is for the theoretical physicists. This is the scattering polarization here in the sodium lines, the orange lines that you see in like sodium lamps. And if you look down here at the polarization, well, this is one crazy scattering polarization. What happens here is it's like a double slit experiment. The photon comes to a sodium atom. It doesn't know whether it should scatter on the D1 or the D2 line. And so there is quantum mechanical interference that then leads to this profile. Nobody expected this peak here. It's only papers in a few years ago that can actually calculate and can explain where this comes from. Really crazy. If you're really into radiative transfer, it's probably one of the most challenging problems in calculations. So what do you do with this? Well, exoplanets, right? Exoplanets are found. Oh, that's interesting. That's a challenge. What could we do? So, well, this is almost the same plot, but now here's the star. Sends out light. Stars are basically unpolarized. If something, starlight goes to, let's say, a piece of dust here, scatters, comes to us, it gets highly polarized. I have a way to see exoplanets. I look in polarization, take away the star because it's unpolarized, and all that's remaining is the exoplanet. Yeah, that took us almost 20 years to get there. So let me show you a few things. Two young stars. Nothing particular, right? Intensity images. I made crosses where the stars are. Now we take our linear polarization imager, and the star goes away, and everything around it starts to light up. On the left here, this is T Tauri, so roughly solar mass star. This is a much heavier star, about 7 solar masses. Suddenly, all of this lights up around it. It's beautiful. We did a lot of work on there, and then went on to a big instrument at ESO on the VLT that's now very regularly used. So that was just beautiful. We could use all this work on solar spectra and apply it to images. And really,
Is that a dot? T Tauri? On the right.
You mean that dot here? Yeah, it's probably some cosmic ray or something like that that's left over. These are still challenging. There's still things, and I'll show you towards the end. If you would turn on adaptive optics, it would all fall apart. So there are real big challenges here to do that, but we figured out how to do this and then applied this to larger instruments and telescopes. I'll show you some of that. Now, the real reason why this is so interesting is that if you have, let's say, dust. I don't mean the dust you find under your bed, but something like cosmic dust, right? That looks something like this here. It's not nice. Now, you know what you do in theory? You assume it's all a sphere, right? And then it's what you call me theory to calculate what the scattering is. Now, if you look at you take this here, you measure in intensity as a function of scattering angle. So Light comes in at an angle, scatters out at an angle. You look at what's in between. This here is the model. Well, the measurements and crosses, the line here, well, that matches pretty well. You look in linear polarization here, completely falls apart. And that's because these things are not spheres, and they're not just not round, but they're also not necessarily completely filled. They may be fluffy, they have some things sticking out and so on. So what the polarization gets you is basically can distinguish some of these things. When you now include the polarization as a function of wavelength, you get the amount of dust you have, you get the sizes, and you get the indices of refraction. So you can also tell the composition. If you only look in intensity, there is no way to distinguish between size and chemical composition. So we use this in other ways. On the left here, you see an HST image of our core bore. This is the star here. They saw some things around it. They knew there was probably some stuff around it. Nothing got published with that data because they didn't know what is real and what is not, what is from the telescope and the instrument. And then we used our instrument here on a 4-meter telescope. Here's the star. And we see this big signal here. So we knew this thing here, our resolution was not as good. This thing here is real. The other things are artifacts from the telescope. But with HST data and ours and the different wavelengths that span, we could actually model what the size of it was. And it looked like nanometer-sized carbon, pretty much what you would expect from a star like this. Right, so it's very powerful. Now, jumping ahead by 15 years or so, we're actually now really able to see polarization on exoplanets. So here's an example, DH tau, companion here, see a clear polarization. GQ Lupi, that's probably a little bigger than a planet. PDS 70, we actually don't see anything. Beta Pic, you see here. So now with the 8-meter telescopes, extreme adaptive optics, we can actually see polarization signals. Interestingly, the polarization signals we have seen so far are way too big. We can't explain them unless we assume there's kind of some ring around the planet. And the ring then has a large area that can scatter and would heavily polarize the light. It's our best explanation so far. But it adds new information. Just as a little side trip here, so we got interested in imaging planets and so on. There was a new instrument that became available at ESO in Chile. It was called MUSE. It's an integral field spectrograph to look at galaxies. Well, we were part of the team and abused some of the science verification time and pointed it at a star that had at least one known planet. Crazy, right? But look at what we got. So we used integral field spectroscopy, high contrast techniques, spectral differential imaging, a whole slew of stuff. But you can see here the purple square, the red square, they're down here. Very nice H-alpha emission lines. Star is completely gone, as it should, if our processing is correct. There are fields around it here. They're all flat, no H-alpha emission at all. And so these were the first observations of planets that are still accreting gas. So you see the hydrogen falling onto the planet, getting shocked, and that creates an H-alpha emission line. So it's called PDS 70, B and C. Everybody likes it now. So exoplanets, for those who are not so much into it, I just want to explain a little bit how difficult it is to see exoplanets. If you would look at our solar system from far away, then Jupiter would be about the billionth of the brightness of the sun, 10 to the minus 9. Earth is at about 10 to the minus 10. It's smaller, but closer to the sun, and therefore it's not the ratio that you would think. So I always find this very challenging, right? I can write 10 to the minus 9. I'm used to that. I can write 10 to the minus 27. But what does it really mean? What does it translate to? And I found this illuminating. So think of the star being Mount Everest. And we're assuming we see it all the way to ground level or ocean level. So what's 10 to the minus 9? Well, oops. That got too fast. There it is. 10 to the minus 9 is the size of a red blood cell. So because optics are imperfect, even in space, well, a star looks about like this. It's a peak with a lot of stuff and light around it. So imagine you had some really accurate way to measure your altitude. And you would look on the slopes of Mount Everest, and you would try to find that red blood cell just by looking at how high above sea level you are. And that's about how hard it is to see an exoplanet. So it's not trivial, takes a lot. What are the enemies that we have here? Well, it's really aberrations, so imperfections in the optics itself, and diffraction, the fact that you have a finite aperture, and therefore you get effects from it. This is a Hubble image of some region, I forgot what, probably some star cluster. But you see that there are no point sources here. Maybe very faint where you don't see it here. But really, they're all the same. They have the crosses from the spiders, and then they have all kind of stuff that goes around it. Right, so that's really the problem. One of the things we started to work on was the very large telescopes, the extremely large telescopes that are now being built. The European one is 39 meters in diameter. You need adaptive optics for that. It's a mirror where you can change the surface to exactly compensate what the atmosphere does. If you don't have that, there's no way you can see an exoplanet. You really need to kind of do the optical trick of like taking the telescope into space. Well, when you have a 39-meter telescope, that becomes incredibly difficult. Just the way to control these things goes like with a significant power of the diameter of the telescope. And so it looked like, this might not be possible. So we put our heads together and like, okay, how could we do that? How we can fundamentally change it? We did it in the lab. It's what we called Fast and Furious, and that kind of stuck. Everybody loves that name. And that's just in the lab. You can see here is like a simulated star with the diffraction rings around it. And then we used our algorithm, and we got this here. From here to here is an improvement in terms of, ability to detect an exoplanet of about 100, because it really makes it exactly the way you want this to look. And then, of course, we thought we had a good thing. Yeah, maybe. But it turns out that because we use the image itself and not some additional optics to measure, it actually turns out this is a fabulous way to check and adjust optics in one of these exoplanet imagers. And many of the telescopes now run this algorithm simply to look at the images that they get and then correct a little bit to really get the ultimate quality of image. It runs on the Keck on Super with the VLT. We never intended for this, right? And suddenly had a very different application where it's used everywhere. Then I found myself next to a colleague who did optics in biology. And he had like this fabulous idea. So when you have, let's say, a doctor suspects you have some skin cancer. Well, what do? They take some knife, cut it out, put it under the microscope. So the question was, could we do something on the microscope so you wouldn't have to cut anything out? Put the person's hand under it and just look. Right? So the issue that you have is that you have to look through the skin. Well, skin, atmosphere, not that different. It distorts your image, it produces problems, and so on. So we actually got funding to from Nikon to basically take their microscope and modify it with adaptive optics so that the laser that illuminates things gets changed in such a way that you get really sharp images inside. Now we thought that was, sounds fairly easy. Just put in adaptive optics. Oh boy. It turns out this is a big thing. I didn't know that we needed a lab assistant. Just prepare the samples and help us with things, run the tunable dye laser, and But in the end, we tested it with with breast cancer cells here. On the left is without adaptive optics. On the right is with adaptive optics. And there's a significant gain in resolution, but it's also an intensity. The reason for that is that if we send a lot of light into the skin, now your skin won't like that. So you have to send in infrared light, and you try to send so much light that you get 2 photons at the same time hitting a molecule, and the molecule then thinks this is visible light. And then it fluoresces, and you measure the visible light that comes back. 2-photon fluorescence. It's a fairly standard approach, but because these 2 photons coming in basically at the same time in the same place, the focus of the laser has to be incredibly good, and we could achieve this. Now, the measurement part was crazy. We had to do all kinds of things, but we managed. Learned a lot. So next thing is, you have seen before when I showed you these laboratory stellar images, you have all these rings around it, the area rings, right? And we started to think, how can we get rid of that? Generally, this is called a coronagraph. You try to make it dark next to the star. And so my postdoc at that time, Franz Nick, he came up with this brilliant idea that we could use liquid crystal devices to achieve that. I'm not going to go into the details. This is basically using geometrical phase instead of your regular phase. The great thing about it is that it's basically achromatic. Normally, when you do things with wavefront and so on, it's always chromatic. With the geometric phase, it becomes achromatic. And so it works over a very broad wavelength range. This is done with laser writing on glass plates and then growing layers of liquid crystal molecules on top of it. So this is not the liquid crystal that you have in a screen. This is fixed. These are fixed liquid crystals. Unfortunately, all these guys now, they were bought up by Meta, and they can't do any of our stuff anymore. But let me just show you how this works. So this is perfect optics here on the left. The image of a point source with perfect optics around aperture. If you go out here, you get a contrast of like 10 to the minus 4. Remember, we want to achieve something like 10 to the minus 9 to see Jupiter around the sun. What we can now do is, instead of having a beautiful optic, we actually on purpose make the optic bad. But we make it bad in such a way that the point spread function, for example, gives this dark area around the star. So the optics are not perfect anymore. The wavefront is not flat anymore like you would think you would want it, but we distort it. We basically engineer what we see in the focal point. And it's basically the same thing as holography. We create something in an aperture, Fourier transform it, and then that's where we want it to be good. On the right side, that was a really astonishing thing, is that if we would know where the exoplanet is, we would just make it dark in an area where the exoplanet is. And that we can achieve a contrast of 10 to the minus 8 very easily with this approach. So it's a very universal thing because you can calculate it and then you manufacture it. And this is not just in theory. This was the first on-sky shot that we had with one of these coronagraphs on Magellan. And immediately we saw a companion here. It was known, but still, it was kind of the people who pointed the telescope weren't aware of it, that it was a binary. And I looked at it, what is that? So this works. And then we went more crazy. And that goes into the direction of, well, What we have here is not perfect. We would like to probably adjust some of the optics a little bit so that we get an even better result, that it gets really sharp. We want to measure that. And so with these holographic approaches, we could go more crazy. So now, instead of just building the coronagraph with the same piece of optics, we also built the device that could measure what the image quality was and how it was wrong in the focal plane. So on the one hand, we have the image here in the center, and then around it, we put additional information. And then the camera and an algorithm behind it, they take these images here, calculate how the optics have to be adjusted to make it better, and then you get what you have here on the right side. Nice dark hole on one side of the star, and you see these have changed here, but that's because now it's perfect. So it's this system thinking. When you look at the first generation exoplanet imagers, be that GPI on Gemini or Sphere on the VLT, they all have a coronagraph that was designed for perfect optics. You have an adaptive optics system that doesn't know about the coronagraph. You have an imager system behind it, doesn't know about anything else. And so what we started to do was really look at this as a system. How can we combine different components and make sure that the whole system is optimal, not the individual components? And that's really why the current exoplanet imagers are limited in what they can do, because they have all these separately optimized components, but together they're not optimized. And then when you do things like that, once in a while you get to do something just totally different, but using exactly the same math. So there's this famous Dutch artist, Dan Rozengaarde. He does light installations. And he had this idea that he wanted to make an artificial rainbow on the train station in Amsterdam. And yeah, you know, that's easy. What do? You take some kind of conic-shaped prism, right? That's how you make a rainbow. Easy peasy. Well, if you carefully think about what a prism does, a prism deviates the blue the most and the red the least. So you would actually, whatever you do with glass, you get a prism that is red on the inside and blue on the outside. Not what you have in a rainbow. So he had this contract, he had to deliver, and he couldn't figure it out. So he came to us and said, I'm lost, what do? I'm screwed. So, well, you know, with a little bit of physics, you know, if you have a grating diffracts the red more than the blue. So we built a set of holographic gratings, made them in Japan, flew them over on a seat. It's like a thing this big, composed, big source of light under it, and made this happen. All right, so sometimes what we worked on here, crazy stuff for exoplanets, suddenly works very well for an artistic project. Ever since that, we had an artist in residence who wanted to do something with light. Always fun stuff. So let me get back a little bit to maybe more the theory here. And don't kill me when I say this, but the Fresnel equations are wrong. For those of you who remember, if you derive Snell's law or the law of reflection on a mirror, you use Fresnel's equation. And you derive them by saying, OK, I have one material here. I have an interface to a second material. They have different optical properties. You get a reflection and refraction on it. Or in a simpler case here, you have a mirror. You have air on top. You go in, you go out. So if you look very carefully in your textbook, whatever optics textbook you want, they all do it the same. Somewhere there's in probably very small letters written, we assume that this interface is indefinitely large along or across this, along this interface, right? Basically, assume the mirror is infinitely large. Well, That's not what we really have. And you might say, is it really relevant? Well, it turns out when we did exoplanet imaging, even on a 4 meter, we turn on the adaptive optics, and for the hell of it, our polarimetry did not work well anymore. And we couldn't figure it out. We saw it on the 4 meter. We spent many observing runs trying to figure out what's going on. Every time we turned on the adaptive optics, it went to pots. And so, yeah, over time, you start to get thinking, what's wrong? And in the end, with my theoretical interests, we said, like, OK, what if the Fresnel equations are wrong? And yes, they are wrong. So if light comes in onto the mirror, the incident angle and the outgoing angle are not the same. And so it's not just that, but the reflected beam may not be in the plane of incidence anymore. And the angles change too. Now, the angles normally in astronomy are not the biggest issue. It's really the position. And it gets really crazy. If you have here on the left, you see that light comes in from the left. It's like it doesn't get reflected there, but it kind of goes across and then comes out. And that shift, that had been seen in physics. It's called the Gauss-Hänschen effect. It was known, but typically for physics, you work with a Gaussian beam that is maybe 1 millimeter in diameter. And nobody really knew, was that even relevant when you expanded it to, meter-size optics, cylindrical beams. And so we went back through all the calculations, did everything from scratch, didn't approximate any of the diffraction. And on the right, you can see the dots is what we get out of physics, and the solid lines are what we are getting out of our calculations. So we knew we were on the right track. It gets really crazy when you have circularly polarized light. So if the electric field vector makes a corkscrew, if it goes onto a mirror, it actually goes sideways and comes out. It gets moved sideways. For those who are into this kind of things, this has to do with the requirement that total angular momentum be preserved. If you have a circularly polarized beam of light that has like a spin, so it has spin angular momentum, but then on reflection, some of the circular polarization is made into linear polarization, so you lose the spin angular momentum. And by going sideways and out, you basically introduce an orbital angular momentum into your light beam. So it's ultimately comes down to very fundamental physics. And again, you might say, well, how is this relevant? Well, so here is the ESO VLT measurement on the left. This is the polarization of a star. This should be 0 everywhere, but you see this like white and dark area, positive and negative signal. This is because the two polarization states of light do not arrive on the same part of the detector because of these shifts. On the right side, you see our simulation. In the middle, blue is what the shifts that were measured on the 8-meter telescope. Red is what we predicted from first principles. There was no fitting, no parameter adjustment, nothing, just first principles. And so this is very relevant. If you look at the Roman space telescope that has a coronagraph built in, they have a polarimeter in there. They still don't know how to use that. Right? Because it's really, this is fundamental physics that has an impact on astronomical observations. So let me get a little bit into other things. Now that we measured dust, we measured, how much dust there is somewhere, what size the particles are, maybe composition of circumplanetary material. Well, we noticed this is the same problem that you have on Earth with aerosols, small dust particles in the air. If you look at the map of Europe here, it's particularly bad in northern Italy, and here, Netherlands, Belgium. In the Netherlands, people lose 1 year of their life because of aerosol in the air. That's largely from ships that have uncontrolled emissions. So very relevant in the Netherlands. We had been asked whether we could make some kind of a detector for a Mars mission to measure dust in the Mars atmosphere from a lander. We came up with a principle, and we were not selected. We kept it in the drawer. Ultimately, it became very interesting to do that from space, because aerosols are the biggest unknown in any climate model. And so we really kind of got into that. We developed a new measurement principle. What you see is the intensity spectrum that you see when you vary the amount of linear polarization. On the right, let's stop play here. If you change the angle of linear polarization. This is a frequency encoding. This is a modulation encoding. So we encode a sinusoidal variation on top of the intensity spectrum that represents the amount and the direction of linear polarization. This has been incredibly successful. This was the first prototype that we built. The thing about this is this replaced an instrument that was roughly a cubic meter in size. This one you can hold on your hands. Previous instruments had many, many motors, very tight temperature control. This has no moving parts, no temperature control needed. So this was a big success. Airbus ultimately picked it up to build an instrument on what's called PACE. It's a NASA satellite plankton, aerosol, and ocean color. I think it's experiment. You can see the size of the thing under the red plate. This is a very, very small instrument now, and performs better than any previously flown instrument. So coming out of astronomy, think about how we can measure dust composition and particle size around stars led to this. These are some of the first data sets that came out. On the left is flying over Japan, on the right over Ethiopia, looking at the kind of the small scale, very small, fine dust, bigger particles, and the amount of absorption. The experts can immediately tell over Japan you have sea salt and urban emissions. Over Ethiopia you have burning wood, basically. So highly successful. And then we had this crazy idea whether we could build the same thing very, very cheaply, like for a few bucks. And so, yeah, we actually managed to build a little device here that does the same thing, used to attach to an iPhone. You can see this was a long time ago. But ultimately, this cost a few bucks here. It was all plastic optics, but we were able to replicate what it does. If you look at unpolarized light, you got something like this. Polarized, you get this modulation on top that tells you the amount of polarization as a function of wavelength. And then we produced 10,000 of these things, distributed them all over the Netherlands, and had people scan the sky with this. And based on that, we could make maps of the aerosol load in the Netherlands. This was our map here. Blue dots is a citizen measuring, and this was the satellite map that was available. That's pretty good. Ours has a lot higher resolution in time and space. It was a fun experiment to involve thousands of people in it. This has now developed into what we call Citizen Science Lab that is doing all kinds of things. Goes to archaeology, language science, and so on, using approaches that we developed on how to get that many citizens involved. I think I'll skip over this, how to find life. Yes, we can with polarization. And I think I'm going to finish with this thing here. This is now going totally crazy and nuts. So this was an idea that I had as a PhD student. I convinced two professors to put in a grant proposal for me. So while I was a graduate student, I had a grant to have my own graduate students in physical chemistry. So when you look with telescopes, whether you look at a planet or the Earth or a star or a galaxy, whatever, really what you would really like to have is for every photon that comes, you would like to know the direction that it comes from, when it comes, what polarization it has, but also in particular what wavelength or energy that it has. Right? If we could tell for every photon what its wavelength is, we wouldn't need a spectrograph, because for every photon, it would tell us what the wavelength is. We wouldn't need a filter. If I just want to have certain wavelength ranges, if I have a detector that can tell me, that's great. Now, your typical detector that you see that is has energy resolution, they get a resolution of maybe 30. So think of 30 band passes across the visible spectrum. I was interested in getting something like 100,000. So how would you do that? The idea was to have a slide film. For those of you old enough to remember what slides are, or film, right? They have 3 or color molecules in it. They're sensitive to colors at different wavelengths, typically 3. Well, what if we could do a film that had 100,000 different molecules, each sensitive to a slightly different wavelength? Well, it turned out, I learned that that actually can be done. And you can create something like this here. This is the wavelength. And these little lines here indicate kind of where a particular molecule is sensitive. The way you do that is you take a molecule that has very high sensitivity to Stark effect. So the wavelength shifts where it absorbs as a function of the electrical environment it finds itself. So you put these molecules into plastic, because plastic is an amorphous environment where you have a lot of different electric fields locally. And then you cool the heck out of it with liquid helium. You pump it, you got super liquid helium. Makes it very nice and stable. And then when you send in light, for example, from one wavelength, then that molecule will undergo a photochemical reaction and will no longer absorb at that wavelength. So if you do this, and the molecule here is a porphyrin ring, if you add iron in here, you get hemoglobin. If you add, what is it, magnesium in chlorophyll? I forgot, I have to say, my physical chemistry is getting bad. This is the simplest version where you have hydrogen. And this is the photochemical reaction. So this is an example here, just taking a tunable laser and burning some what's called spectral holes in it here, just to show that, yeah, you can do that. You send in light at different wavelength, and indeed, the absorption decreases, like you have on a film. So we built a telescope to bring the sun in. And so we exposed this film to sunlight. There was no filter, there was no spectrograph, just this detector, this film. And when we read it out, this is what we got here. You get kind of the inverse of the spectrum, because where you have a spectral line, you have less light, therefore you burn less of a hole. You can, of course, then clean this up a little bit. This is a very famous spectral region around in the red, where you have 2 iron lines from the sun, and these 2 lines are from the Earth's atmosphere. And then we could do this on every pixel here of the solar image. Now, it is a simple thing, just did the solar rotation. We just measured how much of a wavelength shift we see because the sun rotates. And so this is what we got out here, red shifted on one side, blue shifted on the other side, as you should. No spectrograph, no filter. Now, this required 2 labs and a supercomputer at that time. This was in the mid-90s. We needed 1 lab just to run this big tunable dye laser that we needed to read out. And then we had this cryostat in the other one. If you have ever worked with superfluid liquid helium, you have a hole of 1 atom size, it runs out. So it's at that time, it was really tricky to do that. Everything had to work at the same time. And then the computer, because the amount of data, if you get, for every pixel, we had so many spectral points at that time. That was a really large amount of data. It was a fun thing. Ultimately, the reason you don't see this is because it's just, it is complicated to make this work. And like film, it's not linear. And astronomers really didn't like that. So this is probably the most crazy thing I have done. Thank you for your attention.
Okay, great. Thank you, Christoph. And so now we'll open things up for maybe 8 minutes of questions. We try to start with questions from students first. I have a backup plan, don't worry. Okay, if that's the case, we're going to take a page out of Zach Berta Thompson's book right now, and we'll give you 60 seconds to talk to each other, and then we'll come back and see who has questions, if anyone. Ready, set, go.
It's about life. You missed life. In 1 minute. Good. Yeah.
Seems like it's close enough to generate some questions. Okay, so one thing you should know about me is when I give you a certain amount of time to discuss something, I'm not actually counting. I don't pay any attention to the start time. So that is a minute that I just decided happened. Okay, so now any questions for Christoph? There was a lot of discussion. Okay.
So you said it took a supercomputer, a whole cryostat. If you had to do something like that now, would there be something?
A laptop would be fine.
Wow. But what about the film and the actual? Would that remain the same, or is there something better that you can think of that gives you?
We had agreements with industry. If they would find something, we would test it, but they wouldn't tell us what it is, trying to find something better. There's some very, subtle physical chemistry effects and issues that at some point you start to hit. Has to do with the fact that even at 1.2 kelvins, you still have phonons, so acoustic effects basically that mess with this. Right? You don't get a very sharp absorption line, but you get the phonon wing, which is that part of the energy goes into acoustics.
Thanks. Questions from anyone? I'll work my way over.
So the problem with the AO and the messing up your polarization measurements,
yep.
Is that were you able to solve that? Is that a solvable problem?
Let's see. So this one here, or is it the Fresnel equations? Right. This one here. It changes the way you design instruments. Well, you know about these things. Typically, people, like on the VLT, to avoid the telescope from introducing polarization, you cross mirror. So you have a 90-degree reflection like this, and then you do a 90-degree reflection in an orthogonal way. What turns out for this, and that's what you do, like that's what's done at the VLT. It's done at other solar telescopes too. Well, it turns out this is about the worst thing you can do for this. The two effects actually add. And so I think it leads to a new way to think about design. People are thinking about doing 2 AO systems, one for each polarization state. It certainly completely changes the way you think about designing these instruments. And some of it you can do after the fact. You measure one polarization state, you measure the other, and you know there is a shift between them, and just shift it in software. And that's what we're doing right now, and that helps. But of course, the shift is a first-order effect. They're higher-order effects that at some point will bite you.
Thanks. Next question.
Yeah, thanks, Christoph. So, despite what you said, this was still a pretty awesome instrument that made a lot of great observations.
Absolutely.
But is there going to be a follow-up for the ELTs of something like Sphere?
Yep.
Can you talk a little bit about that?
It used to be called EPICS or PCS, and it's It's not a first light instrument for the ELT because as we know from the 8-meter class telescopes, once you put on a diffraction limited imager, particularly if it goes to shorter wavelengths, you'll find all kind of troubles you didn't know about. So we expect this for the ELT too. And so we first want to have the others go and figure out what the problems are and then finish the design.
Thanks. Other questions?
Could you go back to the spectral hole burning slide? Yeah, that one. So could you talk more about those like top 2 profile figures? So is that like a broad band line measurement, and then are those like Watt profiles or something?
So the little things here is like think of it the absorption profile of a single molecule. And then because they're in an amorphous material, plastic is amorphous, every molecule will see a slightly different local electrical environment. And because this molecule is very sensitive to the Stark effect, that means the electrical field will shift, the local electrical field will shift its absorption line. So if there would be no electric field anywhere, they would be all lined on top. With the amorphous material and the locally different electrical environments, it kind of spans out and covers a certain range. It's not the whole spectrum, but you can see that here we go from, let's say, 630 to 636 or so. So it's not that narrow. You have a good number of spectral lines you can cover.
Thank you.
Okay.
Thanks, Christoph. This is such a interesting talk for sure. I have so many thoughts that I'm like, I can't even. The thing that's interesting to me here is, and maybe you can help me understand this, is how do you then, say, apply this to temporally track, right, like images of this, right? Because I'm thinking that the film burns at some point.
Yeah. So there's some interesting aspects of this. One is that if you heat it up, it will like reset. Or you can actually flash it with broadband white light and it will reset. The other thing is that if you take a narrower spectral range, you can apply an electrical field externally. And so if you change that over time, you can make a movie. And actually, my physical chemistry colleagues, they did make a movie of some stick figure walking, all in one film.
Okay, time for one last quick one. Caroline. Okay. Do you have more of the iPhone things?
I do have a few left, somewhere in a moving box, yes.
Okay.
There is no guarantee that it works. We actually have a new version, version 2, that's now, it's basically commercial. We handed it off to a company. We couldn't, really. When you get into plastic optics manufacturing, you learn things you never want to know. So we handed it off to a small company, and they, I think if you go probably to ispecs.nl, it'll probably prop up. I don't know whether they sell it already now. It is a universal adapter, and you can 3D print an adapter for any phone.
Okay, with that, let's thank Christoph again. Colloquium next week? There is Colloquium next week.